Great. Okay, so today we are continuing our talk on, why is this screen not going away? Continuing our talk on relational algebra, and this will be our last day talking about this. We've already covered basically everything, but there is a particular operation, the division, that I want to talk about. And unfortunately, I haven't seen a very good treatment of this, including in our textbook. Our textbook gives examples, but being able to take a query, I'll show it to you now. And after a little bit of a spiel, I'll come back to this and give you some time to work on it. So we have the same four tables, people and some information about them, age, gender, a table of restaurants that people like to frequent, a table of foods that people like to eat, and a table of restaurants in their menus, with a query to find the names of people who frequent only restaurants serving at least one food they eat. Maybe they're picky eaters. They don't want to go to a restaurant knowing that there's nothing that they like there, so they avoid those places. And the tricky word here is this word only. Only for all these types of words are, I think, part of the most complicated SQL queries. And I don't just want to show you the question, show you the query, and then show you how the query resolves this question. Because really, the hard part is how do you get from one to the other? So I spent some time trying to think about a more systematic way to approach this, and that's why we're taking a little bit of a step back and talking about quantitative reasoning. I'll remind you that there are three types of basic logical operators: the and, the or, and the not. And I've drawn truth tables here for each of them. In the case of and or, a truth table when there's two variables, x1 and x2. And for the not, just a single variable, along with their values. I think that this is fairly straightforward. I won't go over it again unless people ask, but I think that this is something that you should have already been exposed to before in your programming classes. What you might not have been exposed to are these things called predicates and how they're formed. So the last class we sort of ended by discussing De Morgan's law, which is fairly straightforward. Basically, it is a way to distribute a not in a clause, where here a clause is made up of predicates and basic Boolean operators, ands and ors. So the way that it gets distributed is it negates each predicate, and it flips ands to be ors, and in the case that there's an or inside of the clause, that gets flipped to be an and. So pretty straightforward, but I proved this in the case of the and I left it as an exercise to do it with the or. Is that something that you guys were able to do over the weekend? Okay. Some people are having trouble logging on. Uh, Karina, are you saying that because you're being told by some other medium that people are having trouble logging in? Right, is okay. Is it just stuck at the loading screen?
Oh, hi, Professor. It's Karina. I think Brian's having trouble logging on. I'm not sure if other people are also having trouble, but I'm okay. I can hear and see your screen clearly. So,
Okay.
mm.
Thank you for letting me know. Yeah. So of course this was an issue last Thursday. I was in a class earlier today where it seemed like it was doing fine. I don't think it should be my internet connection. I mean, we have a fiber optic here, which is really great. Um, uh, let's see. Okay, just a minute. I don't know if I can share. I can have multiple apps since the link is faulty. Yeah. Oh, I see Brian is in here now. And now he's not. Okay. Well, I'm going to try this anyhow. Sorry, I'm going to try to create a Google Meet, and I will share the link to that on Blackboard. And I'll try to do both simultaneously. I haven't used Google Meet before. In particular, I don't know about the recording feature. I guess given this point in the semester, I'd like to not switch platforms, but let's see. I'll try it and see what happens. You think Blackboard has its own tool? I mean, I have a separate. Oh, Blackboard. Yes, that's right. Blackboard does have its own tool. Uh, yeah. Well, let's see. Okay, let me try the Blackboard. So I have to move things around now. Okay, I think I'm almost finished here. All right, well, if people do have issues with WebEx, yes, there's also a Blackboard Collaborate that is running as well. Yeah. So I'll do this for today and the next class. I'll try to have both. I guess I would prefer that people try the WebEx first. But yeah, again, for recording, I don't know how to do that in Blackboard. I'll have to play around with it some. But I guess we'll just go like this for now. Oh. Basic quantitative reasoning. Okay. All right. Well, I see Brian joining the Blackboard Collaborate. Okay. All right. Sorry about that. We'll see. We'll see how it goes. Where's the chat in this? Just in case Brian has something to say. Chat. Oh. There. Now my audio is being shared. Okay. So, great. Let's continue. So, De Morgan's law. We will be coming into this later with an application. So, there are also these two. Sorry, I'm just gonna. This. Oh boy. It's complicated. Okay. Sorry, I had to make some of my windows translucent so I can see all of these meeting things. Okay. So there's these two quantifiers. Let me get this here. These things are called quantifiers. And there's only two of them. There is a there exists and for all. So the basic idea behind these is pretty straightforward. These are quantifiers that are applied to make a statement either true or false about a set of things. So here I've drawn a set as a big circle and elements of that set as being smaller circles. And the way that the for exists quantifier would be true is it looks at every single element in the set, or this will be at each tuple in the relation or at each row in the table, and it applies this statement to each one. And if it's true for a single one, then this is true. Otherwise, it's false. For all does the same thing for given a set and elements of that set. The statement is applied to every single element of that set. And for every single one, it must be true for this to be true. Otherwise, it's false. So here is an example where these start to get mixed together. There exists a day this week that rains every hour. So there's 24 hours in a day, 7 days a week. I'm sure that this is obvious, but I'll ask it anyway. What needs to be true in order for this statement to be true?
It needs to rain every day. No, every hour.
Okay, and what does that mean, every hour?
Periodically. Like it needs to rain periodically throughout the day.
Can you be more strict? What is periodically?
Every 60 minutes. Once every 60 minutes needs to happen at least once.
Okay, for how many 60-minute periods?
24.
Okay, do they need to be consecutive?
Yes.
Correct. Okay, that's right. So at least one day needs to rain for every hour that defines, for each of the 24 hours that defines that day in the week.
Mm-hmm.
Okay, excellent. Thank you. So, well, let me leave that. I'll copy this a little bit. There must be at least one of the 7 days in a week that has some type of rain in each of the 24 hours that define that day. Okay. Now there's lots of ways that this could be false. So now I want to take this statement and negate it. So I'm just going to do that this way. Not, there exists a day this week that rains every hour. Actually, before I do that, this will be a little bit easier if I rewrite this statement using quantifiers. So there exists a day this week where for all hours in that day, it rains. Okay. So this is another thing that I think you might find useful, is taking English sentences that are well phrased in English and trying to make them a little bit more concrete, particularly using there exists and for all. So here I'll remind you that there exists is written with this backwards capital E, and here I'm interpreting every hour to be for all hours. The for all is written with an upside down capital A. Yeah, Eric is asking, when we say it rains every hour, does raining 15 out of 60 minutes consecutively count as raining every hour, or it needs to be the full 60 minutes? This statement isn't clear enough to say, but certainly there should be some rain for some part of every hour in that day. Otherwise, certainly you can't say that it rained that hour. So, yeah, this statement doesn't give enough information to say that. But for the purposes of this class, yeah, that would be fine. Okay. Now, well, I guess I'll keep those. I don't want it to get too messy, but okay. Now, here I've just wrapped this statement in a knot. I want to try to come up with the logical opposite of this statement. So, logically, what should be happening is there's some truth space, and there's some space where the statement is true, and everything else is where the statement is false. So here the statement, there exists a day this week when it rains every hour, is inside this true bubble. And now I'm just trying to come up with a statement that would get everything that is logically inconsistent with that. So how would you think about trying to rephrase this? Where, yeah, Is there, I don't know, maybe a more English type of way that you would phrase this sentence without using the not? Okay. I'll give you another minute. Yeah, Jamie says, for all days this week, there exists an hour that it rains. There's some things you're doing right, but not everything with that. Let's see. Dan says, there is no day in the week where it rains every hour. Yeah, that's probably decent for English, yeah. Any day this week that does not rain every hour. No, not quite. There is at least an hour of no rain each day this week. That would work. All days this week do not rain every hour. Yeah, okay. So a lot of these are pretty close, especially for the way that I'm asking the question, which is how would you phrase it in English? For this, let me copy one that looked reasonable. No day exists this week such that it won't rain every hour. Yeah. Again, so Francisco, you're doing some things right there for my next question, but not quite, because those it's a little bit like Jamie's response. Some things are right, but you're missing something with the logic there. So I don't know. I'll just choose Lydia's. Here, there is at least an hour of no rain each day this week. No, won't. No day exists this week such that it rains every hour. That would fix it. Yeah, yeah, that would fix the English part of it. So, yeah. So let me go back to the blue sentence here. There exists a day this week where for all hours in the day it rains. The way that this breaks down is saying that there exists for all and then a statement, where the statement is it rains. This is Q. So kind of like De Morgan's law, and this is where Jamie picked up on something very good. This means not there exists. This is the same as saying for all. And not for all implies that there exists. So if I say that all cows are black and white, then this is a for all statement. One way to prove that statement wrong would be to show the existence of a cow that's not black and white. If somebody presents a brown cow, then that is a way to negate the truthfulness of the statement, all cows are black and white. And saying, let's see, so for exists, well, this sentence here, like there exists a day this week when it rains every hour. If that's not true, then it means for all days in the week, it was not true that it rained every hour. So applying this to the statement above would be that for all days this week, there exists an hour it did not rain. And so, Jamie, this is the part that you missed. You said for all days this week, there exists an hour that it rains. But that statement doesn't disprove that there was one day where it could have rained the entire day for all hours. I mean, it could have rained some hour each day of the week, but for one day, it happened to rain all day, all 24 hours. So your statement, for all days this week, there exists an hour that it rains, does not contradict this statement, that there exists a day this week that it rains every hour. But if for all days this week there existed an hour it did not rain, then it cannot be the case that there is a day this week where it rained every hour. So this is for all there exists, not Q. So here the not gets distributed to there exists, to, and it, right, well, I don't want to make it too messy. I think I've made my point with this. But let's see, let me scroll down. Got it. Okay. From what I've said so far, and I know that this isn't a philosophy class, but are we on board? Is everybody following? Do you have questions? Did I lose you somewhere? All good. Excellent. Okay. So, this is the type of thing that we will be trying to do to break down some of these queries in relational algebra. And the problem with relational algebra is that it does not handle this for all. So for all statements are something that natively relational algebra doesn't deal with. So you have to employ this trick here in order to make your queries work. So it's a lot of negations and things like this that are required. I'll ask one last simple question. Let's see. How can I take a logical statement and apply an operation to it such that its meaning doesn't change? So I'm asking something obvious, but I don't want it to be misinterpreted. So this would be a question of the sort, in addition, what kind of thing can you do to make the number not change? Well, you can add 0. Well, in multiplication, what operation can you do such that the number doesn't change? You can multiply it by 1. So this is my question. We've seen everything in this so far that you would need. Like, if I have a logical statement, Q, what operation or operations can I do to it such that it doesn't change? So 0 plus any number is any number. So if I asked, in addition, what operation can you do that doesn't change the number, you add 0. In multiplication, it's multiplying by 1. Oh, I'll just put x. X. That leaves the number unchanged. So now I have a statement Q, and I want to do something to it such that it doesn't, the truth of statement Q doesn't change. And it's not complicated. Yeah, I guess, well, the OR operator might work, but yes, negate it twice. That's what I was going for. So not Q equals Q. So if you take the truth value of something, you flip it, and then you flip it again. Yeah, not. Correct. Okay. So that is what we will be doing here. All right. I will move on. So we come back to this question. Find the names of all people who frequent only restaurants serving at least one food they eat. Um, let's see. Let me bring up something here. So again, I don't want to just lob an answer at you. So here, I want to try to break this statement down into another statement that uses there exists and for all. Any guesses? Okay. Okay, I'll give this one to you, and yeah, maybe with a bit more practice. For all restaurants X, this person goes. There is the property that there exists food Y such that P food Y such that P likes to eat Y and X serves Y. Make that a bit bigger. Okay. So please read this. For all restaurants X this person goes, you can even get rid of this. There is the property that you actually don't need that. Make it simple. There exists food Y such that person P likes to eat Y, and X serves Y. Can you agree that this statement is capturing the same meaning as this sentence? If you agree, say yes. If you disagree or are confused, please say so. Okay, great. So, now, so just to emphasize again why we're going through all of this, it's because these for alls are something that relational algebra and by extension SQL doesn't handle natively. The reason for this is because the select statement, which is looking through the rows of a table and sort of crossing out the rows that don't apply, and keeping what makes its way through the filter, that's done in a way where the select statement is looking individually at each row and really has no memory. But when you're asking a question, is it true for all of the table? Then that starts introducing the concept of memory, and that should be avoided. So, let's see. Where? A common way to think about this is that you have some statement Q, and this is going to have two knots, not Q. And this knot is going to be changing a for all to a there exists. And this knot is going to be a set difference. Okay, so this inner knot allows you to do a select, and then you deal with the outer knot by doing a set difference. Okay, so this is why I'm introducing this notion of statements and double negating things. It's because we know how to do set differences, and we know how to check for there exists statements. That's using sigma, maybe pi, really it's sigma, to check the truth of individual rows. Okay, so that's sort of where we're headed. Okay. And so we don't like for alls. For alls need to be changed into there exists. Now, let's take this statement and we'll negate it twice. Not, and then this statement. Okay. I would like to see if for this inner knot, this one. How would you phrase this? So you're applying in the same way here that we took this statement and applied a not to it to come up with another statement. So there exists a day this week that it rains every hour. The opposite of that statement is that for all days this week, there exists an hour it did not rain. In the same way that we did that, can you apply that to this inner knot? So, I'll say in English. In English with quantifiers. Let me get my timer up. I'll give you guys 2 minutes from the time that I actually open up this app. Okay, 2 minutes. P is person P. Yes. Are you listening to my class? You learning stuff? Yeah, I like this class. This is fun. Now I'm finally teaching what I came up with. No, like that. Okay, I see 2 answers so far. Brian, you are very close. it looks like Tushar has a good answer. Yeah. Okay. Let's see, Matthew. For all restaurants, X person P does not visit, there exists food Y that P likes, and X does not serve Y. Not quite. There exists a restaurant X that person P goes to, such that for all food Y, P does not like to eat X, or X does not serve Y. Yeah, Pranav, that works. Yeah, so these just take some practice. I'll try to come up with some more practice problems for you guys to work on this, because it really does just take some practice. But here, this for all is going to become a for there exists. This there exists becomes a for all, and this such that is the select part of the query. So either, so this is a not P and Q, and so De Morgan tells us that this becomes not P or not Q. So that's this part. So this statement becomes there exists a
Professor, if you're speaking, just know you're muted.
Oh. Thank you. Yes, I was speaking. Okay, great. So I see that yes, Tashar's looks good. Brian, your answer looked very good, except the very last part of it. X serves Y. That should be the person does not like to eat, or X does not serve Y. For Matthew, for all restaurants, this person, it should be does visit. There exists a food Y that P likes. No, yeah, that's not quite right. Prinav, your answer looks good. Restaurant X. Right. So what I was saying was I will try to give some more practice problems with this, because I think it really does take a little bit of practice. And it's good to try to think about what the actual logic is and what would negate it, I guess. Most of the time, well, many times in logic, you can tell by comparing two statements if they're really saying the same thing or not. If that's something that you have trouble with, you can try practice, or if you have like specific questions, maybe you can come to my office hours this week, and I can try to help you navigate how to go through it. But the interesting parts here are this for all. That gets changed to a there exists. This there exists gets changed to a for all. And this P likes to eat Y and X serves Y is this sort of De Morgan-like statement. So this is a P and Q statement, and we're applying a not to it. So this turns into there exists a restaurant X this person goes, such that for all foods y, p either does not like to eat y or x does not serve y. Some of your guys' phrasings were right. I see Tushar looked like he got it. Same thing with Pranav. And yeah, okay. So far so good, I hope. Okay, now with this statement, there is a problem with it. Not logically, but there's a problem with this as far as querying is concerned. We're trying to come up with a way to represent this statement in relational algebra. Can anybody spot it? Oh, so for this, okay, let me do this. Equals not. I'm really trying to just take this inner part though, so I don't want to do that. Yeah, right now I'm just focused on this inner not part. It uses for all, correct. Yes. Thank you, Jamie. So here, there's still a for all part of this statement. And that's something that that's a problem for relational algebra. So we need to go deeper. It's like Inception. Just keep going down in the layers until you hit bottom. So let me make a note. This is still a problem in relational algebra. So we'll just apply the same trick. So two nots. We're not changing let me do it this way. So this here, we're going to deal with this with a set difference. So I'll just put that here. Set difference of this. That way each line is logically equivalent to the one above it. Okay. Okay. So now we're going to take this same thing. Let's just focus on this part here, and I'll copy and paste it later. So here, for all foods y, either does not. So we're going to be applying 2 knots to this to keep just this part logically equivalent. And this outer knot is going to be a set difference. And now we're going to try to rephrase this one. So, highlight it again. Okay. So I'll give you another minute. Because this is shorter, I think you'll hopefully be able to get there a little bit sooner. Okay, so for the sake of time, I'll just go here. There exists a food y that P likes to eat, and X serves y. Yes, that works. So there exists a food y that P likes to eat, and X serves y. Okay, so now let's try to build this. So that's it. I'll very quickly go over the whole thing again. So we started off with this statement. For all restaurants X this person goes, there exists food Y such that P likes to eat Y and X serves Y. Because of this for all, we are doubly negating this in this step. So a double negation does not change the truth value of any statement. Now, this outer negation, the first not, we're going to be dealing with that with a set difference. The inner not is being used to change for all to there exists. For all statements are a problem in relational algebra, but if you negate a for all statement, you can turn it into an there exists statement. So the outer not is a set difference. The inner not changes the for all to a there exists. This inner statement then becomes rephrased to be, there exists a restaurant X this person goes, such that for all foods Y, the person either doesn't like to eat that food, or the restaurant doesn't serve the food that they like. For all of the foods that that restaurant serves, or this is a person who only goes to restaurants that serve nothing they like, or serve only things that they don't like to eat. So, okay. The problem with this, though, is that there's still a for all statement. So this first, there exists food Y, becomes a for all foods Y. And so we need to go one level deeper and apply this double not tactic again. The outer not is going to be handled with a set difference. The inner not turns into a there exists statement. So the whole query is going to be, it's going to look something like this: a set minus a set minus a there exists statement. Okay? I'm hoping we have enough time to finish this query in 5 minutes. Let's start with the exists statement. There exists a food Y that P likes to eat, and X serves Y. I'll copy this up here. Let's see if I can zoom out so you can actually see the tables here. Okay. Let me move this over. Okay, so given these 4 relations, first try to come up with a statement for this. There exists a food Y that a person likes to eat, and X serves Y. What is the relational algebra query for just that part? Any guesses? Still working. Okay, because it's coming up towards the end of the class, I don't know if I should leave this as an exercise or give you guys the query to have some between now and our next class to kind of mull it over. So because it's coming up to the end of class, if you want to keep it as an exercise, you can just log off when class is over. For those of you who would like, I can present the query and just the query itself, and you can take some time to think about it. Does that sound okay? All right. Okay, so this is what the query looks like. Yes, yeah, we'll go over it next time. I won't explain it, but I think I've given you all of the mechanics. You can figure out which parts fit to what. And yeah, I'll give another practice problem that's related to this. Again, before class, I'll give this as a practice problem, and I will go over that next class too. So that's it. Yeah, here we have a couple projections, and this is doing basically an inner join. Yeah, I know this was a harder class. I think that, yeah, there's some queries like this. I would have been very, very surprised if I had asked you to go directly from this type of statement and you being able to derive this type of query. So I wanted to make it well motivated. Yeah, I hope it works. Yeah, it took a little bit of thinking about how to try to do it in a more systematic way. So I hope it's helpful.